In this lecture, we will define what is capacitance and we will try to see how to calculate the capacitance for given simple geometries. So you have seen that if there is, let us say, an isolated conductor, so if I give a charge q on it, so what will happen? This charge will spread on the surface of this conductor uniformly, and because of this, the potential of this conductor will be, let us say, V, and this conductor is as of now isolated, means there is no other conductors, nothing in the vicinity, and at infinity the potential is 0, the reference is at infinity. Now if I increase this charge by a factor k, so you see that this voltage will also rise to kV, means by the same factor k. So you see that this factor q over V is a constant. This does not depend on this charge as well as the voltage. This constant just depends upon the configuration of this conductor and the media in which it is present. So this constant is called as capacitance, and its value just depends on the geometry of the conductor and the media. So we can define capacitance from this ratio as the electric charge that must be given to the conductor per unit rise in the voltage of the conductor. So for a given rise in the voltage, if we need higher charge to get this rise in voltage, it implies the capacitance of that conductor will be higher. Similarly, if I need just small charge to get a big boost in the voltage, then the capacitance of that conductor will be small. So this is the definition in the case when this conductor is isolated. But we will find that if I bring another conductor, so let us say this is the first conductor and there is this another conductor. So if I put plus q charge in this conductor, so what will happen? Some charge will get induced in this conductor, minus charge will get here, and remaining plus q will be here because this conductor is already neutral. So because of this redistribution of the charge will happen in this conductor. So now to get the same rise in the voltage of this conductor, we need more charge to be put, because this opposite charge induction will try to lower down the voltage increase. So to get the same voltage increase, we need more charge. So you see that the capacitance has increased in this configuration. We need more charge to get the same voltage rise. So this C has increased in this configuration. So practically this is made use of to make capacitors, because these are energy storing or charge storing devices, and we need that they store a lot of charge for a given voltage. So when there are two conductors, the definition of this capacitance is modified to the charge on the positive plate divided by the voltage difference between these two plates. So this is, let us say, plate 1 and this is, let us say, plate 2. So we will give plus q charge on it and minus q charge on it, and let us say its voltage with respect to infinity of reference is 1 and its voltage with respect to reference is 2. So V12 will be the voltage difference between these two plates. So according to the definition, between these two conductors, the capacitance will be the charge on the positive plate over the potential difference between these two plates. So this definition now gives us a hint or an idea how to find the capacitance of a given configuration. So let us see how we can calculate the capacitance for a given configuration. So what we will do, we will follow these steps usually. The first step will be, we will choose a required coordinate system. According to the geometry, we will see which coordinate system will facilitate our calculation. The second part will be, we will assume plus q charge on one plate and minus q charge on other plate. Now either using some Gauss law if the geometry permits, or by some other method, we will try to calculate the field due to this charge. Then we will find the potential difference, which will be given by minus E dot dl from 2 to 1. Now since we will know this V12, we already assumed that this is Q, so we will find the capacitance as Q over V12. So these are the 5 steps which we will try to follow to calculate the capacitance of a given configuration. So let us try to solve a numerical example in the next slide. Let us say we are given a coaxial line or cable where the central core is the conductor, and then there is this insulation made of dielectric. So let us say this is Ri and this is Ro. Now this is the cross section. If I try to see longitudinally, what will I see? Let us say this is the same cylindrical cable, and let us say its length is L, and at the center is the conductor. Now we want to find the capacitance of this configuration. We will assume that the end effects and fringing are not that large, and we will assume that we will solve within the cable where the end effects are negligible. So what we will do, we will make a Gaussian surface. First we will assume plus Q charge on the conductor and minus Q charge on the outside sheath, which is grounded, and here this is dielectric constant epsilon, or permittivity given as epsilon is equal to epsilon naught epsilon r. Now we need to find the capacitance of this configuration. So we have assumed that this Q charge per unit length is on the conductor and minus Q is on the outside, Q charge coulomb per unit length. Now what we will do, we will make a Gaussian surface, because there is this cylindrical symmetry if we neglect the end effects, and we will choose cylindrical coordinate system, because the symmetry shows that cylindrical coordinate system will help. So the field will be in the radial direction, and it will be the charge per unit length 2 pi epsilon r, where r is the radius of this Gaussian surface cylinder. So this is the electric field intensity between these two plates of the capacitor, that is the inner conductor and the outer sheath, which is grounded. Now we need to calculate the potential difference between the, let us say this is 1, this is 2, between these two. So we will go from the outside plate, which is sheath, which is grounded, to the inside conductor, and dl is now dr here. So we will find that it is equal to q by 2 pi epsilon l dr over r, and we will go from r naught to ri. So v12 will be q by 2 pi epsilon l natural log ro over ri. So this is the potential difference. So the capacitance of this configuration is q over v12, which is simply now 2 pi epsilon l natural log b by a. So in this way we can calculate the capacitance of a given simple configuration. Let us try to find the capacitance of an isolated sphere. So this is a sphere of radius r. So now we will give plus q charge here, and this is isolated. Okay, so the potential will be q over 4 pi epsilon naught r. So the capacitance will be q over v is equal to 4 pi epsilon naught r. So for an isolated sphere, the capacitance is simply 4 pi epsilon naught r. If this media was having permittivity as epsilon, then it would be just 4 pi epsilon r. So in this way we can use those 5 steps to calculate the capacitance of simple configuration. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group for doubt discussion, whose link is given in the description of this video. Thank you.